Welcome back to the channel where we dive deep into the wonders of the universe. Today, we're tackling one of the most mind-bending questions in science. What's inside a black hole? These enigmatic voids have fascinated humanity for centuries, from ancient philosophers pondering the stars to modern physicists wrestling with quantum paradoxes. Buckle up, because this isn't just a quick explainer. We're going on an epic journey through history, theory, and the latest discoveries. By the end, you'll see why black holes aren't just destroyers. They might hold the keys to understanding reality itself. Let's jump in. Imagine a place where gravity is so intense that nothing, not light, not matter, not even information, can escape. That's a black hole in a nutshell. But how did we come up with such a wild idea? The concept traces back to the 18th century. In 1784, English geologist and astronomer John Michell proposed the existence of dark stars, massive objects whose gravity would trap light, making them invisible. He calculated that if a star had the density of the Sun but was 500 times larger in radius, its escape velocity would exceed the speed of light. French mathematician Pierre-Simon Laplace echoed this in 1796, suggesting these stars could be detected only by their gravitational pull on nearby objects. Fast forward to the 20th century. Albert Einstein's 1915 theory of general relativity revolutionized our view of gravity, describing it not as a force but as the curvature of spacetime caused by mass and energy. Just a year later, German physicist Karl Schwarzschild solved Einstein's equations for a spherical, non-rotating mass, revealing a bizarre solution: a region where spacetime curves infinitely, now known as the Schwarzschild black hole. Black holes aren't born from nothing. They're the corpses of massive stars, or the result of cosmic cataclysms. Let's break it down. Stars shine by fusing hydrogen into helium, releasing energy that pushes outward against gravity. When fuel runs out, smaller stars like our Sun puff up into red giants and shed layers, leaving white dwarfs. But for stars over about 8 solar masses, the core collapses violently in a supernova explosion, blasting outer layers away. If the remnant core is between 1.4 and 3 solar masses, it becomes a neutron star, a dense ball of neutrons. Above that, gravity wins, crushing everything into a black hole. Picture this. The core implodes at a quarter the speed of light, compressing to the Schwarzschild radius in milliseconds. The event horizon forms and poof, black hole. Supermassive black holes, like the 4 million solar mass beast at our galaxy's heart, likely form differently. Theories include direct collapse of massive gas clouds in the early universe or mergers of smaller black holes over billions of years. Recent 2025 discoveries, like the direct collapse black hole candidate from NASA's Webb telescope, support the idea of heavy seeds, black holes forming rapidly from collapsing clouds without stellar intermediaries. Mergers are dramatic too. When two black holes spiral together, they emit gravitational waves, ripples in spacetime detected by LIGO since 2015. In 2025, scientists announced the biggest merger yet, involving black holes hundreds of solar masses apart, shaking the cosmos. Black holes grow by accretion, sucking in gas, dust, or stars. This forms a glowing accretion disk, emitting X-rays as matter heats up before plunging in. Now, the big question: what's inside? To answer, let's approach one step by step. From afar, a black hole acts like any massive object. Its gravity orbits planets or bends light, just like a star. But get closer and weirdness ensues. First, the photon sphere at 1.5 times the Schwarzschild radius, where light can orbit unstably. Photons skim the edge. A nudge sends them spiraling in or out. Then, the innermost stable circular orbit, ISCO. The last safe parking spot for matter, at 3 times the radius for non-spinning holes. For rotating black holes, most are, due to stellar spin conservation. There's the ergosphere, an egg-shaped region outside the horizon where spacetime drags you along, like a cosmic whirlpool. Here, the Penrose process lets you extract energy by tossing matter in and stealing rotational kinetic energy. A2C91e. Now, the event horizon. Cross it and you're gone. For an outside observer, you never quite reach it. Gravitational time dilation slows your clock. You appear frozen, redshifting into invisibility. But from your perspective, You sail through smoothly, no bump, no sign, thanks to relativity's equivalence principle. Inside, tidal forces spaghettify you, stretching vertically, squishing horizontally as gravity pulls harder on your feet than head. For stellar black holes, this happens before the horizon. For supermassive ones, you might survive crossing but not long. At the center, the singularity. According to general relativity, a point or ring for spinning holes of infinite density and curvature, where laws break down. Time ends, space-time ceases. But is that real? Quantum mechanics says no, singularities are unphysical. In 1974, Stephen Hawking dropped a bombshell. Black holes aren't eternal. They evaporate. Using quantum field theory in curved spacetime, he showed virtual particle pairs near the horizon can separate. One falls in, the other escapes as Hawking radiation, carrying energy away. The black hole loses mass, shrinking until it pops like a quantum firework. Medium.com. The temperature? Inversely proportional to mass. Cold for big holes, microkelvins, hot for tiny ones. A solar mass black hole takes 10 to the power of 67 years to evaporate, longer than the universe's age. But this creates the information paradox. Quantum mechanics demands information conservation. If you throw a book in, its data should persist. Yet Hawking radiation seems random, thermal, erasing info as the whole vanishes. Is information lost, violating unitarity? Hawking initially said yes, but most physicists disagree. Resolutions include black hole complementarity. Outside observers see info in radiation. Infalling ones see smooth horizon. But this clashes with quantum cloning bands. Firewall hypothesis, 2012 to preserve info. A firewall of high-energy particles at the horizon incinerates infalling matter, resolving paradox but violating smooth crossing. So what's inside a black hole? According to general relativity, a singularity. Quantum theories suggest fuzzballs, firewalls, or even a baby universe. Recent ideas propose our cosmos is nested in one, explaining expansion and dark energy. We can't peek inside, info can't escape, but paradoxes force us to rethink physics. Resolving them could unite quantum mechanics and gravity, unlocking quantum computers, wormholes, or multiverses. Black holes remind us. The universe is stranger than fiction. What do you think is inside?
Comment Bilo?
Subscribe for more cosmic deep dives. Until next time, keep wondering.